Okay, welcome to this installment of class where we are going to discuss something incredibly important, the process statement. In fact, using processes inside VHDL is just an integral part of designing with VHDL. We've held off on discussing processes until we get our handle on some of the basics like data types and doing concurrent statements within architecture and basically fundamental signal assignment stuff, so that we could have a good foundation to start the process discussion. Processes are incredibly important, like I said, but they're also oftentimes misused. And I think that's another reason I like to hold off on process discussions, so that people can see the capabilities and variety of the language without relying so heavily on processes. So here's the rub. Most people who start getting into VHDL come from a background of programming. So they've had some language experience in the past, and they've programmed in languages like C and C# and all the variety of languages out there that we can use to describe designs in a sequential manner, but they're not necessarily used to describing designs as hardware, and that's exactly what VHDL is doing. So you'll see some new folks trying to describe complete designs in a single process, as if VHDL is a language-based system, which you just start pouring your basic language stuff, and then you're done with it, and don't worry about all the other things. And that's a mistake. So what we want to do is we want to approach processes as an incredibly valuable tool for creating super complex logic. And especially for creating complex sequential logic like state machines. But we don't want to ever lose sight of the fact that we're describing hardware. All right, so let's just get started on looking at some basics. First of all, the process statement itself looks a lot like the statement that you're familiar with an architecture. It's a self-contained block, if you will, in the design. I oftentimes think of processes in my block diagram of a system as a single block with inputs and outputs, and it just is a standalone unit in our design. So the process statement basically should always start with a process name. Now, the process name itself describes what the process will do. So naming the process is an important part of your design and making your design more readable and understandable for others. So give it a reasonable name, like signal driver of some kind, or counter, like if you're doing a signal count or element count or something of that nature. So you want to make sure to give it a name that has some meaning to the overall design. It's not required by the standard, but it is an exceptionally good idea to name your processes. So you really should try to name all of your processes. Then we come to the keyword process, which identifies this as a process. Processes typically are followed by a list of signals called the sensitivity list. Now, the sensitivity list itself is a valuable thing because it's what tells the process to trigger. It's what triggers the process into action. We're going to talk more in later videos about this idea of a delta cycle and about how processes trigger and then what that means as far as generating logic. But for now, recognize that the process won't execute. It will not evaluate anything unless a signal in the sensitivity list has been triggered. Now, we've already seen the use of processes in test benches without sensitivity lists, and we'll talk about that at the end of this discussion. But for the most part, processes in a design will have a sensitivity list, and that sensitivity list represents the signals that, when they change, will trigger the process. So if any of the signals in this list change values, like go from a high to a low, or low to a high, or numerically change values if it's an integer, that is something that triggers the process and causes the process to execute. The other characteristic of a process that's important is it must terminate. It must either suspend or terminate. So it either has to finish completely or it has to pause using a wait statement. these two conditions are important for it to be able to generate hardware. And so that's why they have that criteria. So no infinite loops. You can't create an infinite loop inside a process. It just won't work. That's not how processes work. So it's not like other programming constructs, right? So this one must end or suspend in order for it to work properly. The other thing I want to address here is the the variables, okay, the use of variables. Now, it is somewhat confusing when you're new to this. The signals that we've been describing before really refer to wires, and if you can think of them as wires anyway, in the design, where they connect one part of the design to the other part of the design. They typically they're physically manifested as traces or pathways in your design. Variables, on the other hand, are a different animal altogether, and a variable can only be declared inside a process or a function or a procedure, which we'll talk about later, but they're only defined inside the process, not outside. You can't define them in an architecture, for instance. They have a very special function, and they have very special characteristics, which we'll talk about in a little bit. Also, the other very big difference here is we stressed in the early part of the fact that we had concurrent statements in our architecture. This definition region inside of a process is purely sequential, just like a regular program would be, like if you're programming in C. So commands execute from the top and they work their way down, and that's the process. So it is a sequential set of statements, just like you're used to in coding. This is what draws people into using a single process for a whole design. Is it looks a lot like something they're familiar with. It's a program. Yes, let's do in there. I know how to program, and so we'll just get in there and write that. And then that tends to lead to designs that are incredibly inefficient, both in hardware and in the ability to clock at a reasonably fast rate. So we want to be aware of that this sequential nature inside the process, and then there's a reason for that sequential nature in designing and developing hardware. All right, let's go ahead and look at the next part. Whereas we've talked about the fact that we have sequential statements that can be used inside our process, but the interesting thing is they're different statements than you can use outside a process. So only inside a process, or as we'll find later, functions and procedures, can you use these types of statements. There are three main categories of statements for this. One is the standard if statement that you would see in most languages, high-level languages. We also have a case statement that we can use inside VHDL, and we'll make great use of that actually when we do state machines and stuff a little bit later. And then there's obviously a for loop, which allows you to do an iterative loop through a series of algorithms. What you need to scan something 16 times, or if you're scanning all the bits of some vector, that's something that's going to be capable of doing with the for loop. Now, there is a while loop construct in VHDL, but I'm not covering that, and I recommend, especially for those starting out, that you stay away from it. The while loop is heavily constrained because in synthesis, and remember, this course is really focused on synthesis, right? So we're really looking at how to synthesize designs, and in the while loop, you have to be really careful because the terminating conditions in a while loop must be known at synthesis time. So when the design is laid down in hardware, you can't just have it depend upon some input value or input variable like you could with a program. So it's different. And I think for the most part, I've not found a real big use for a while loop that I couldn't easily do with a for loop structure in my design descriptions. So we're just not going to cover that here. There's lots of other places you can look it up if you're interested, but if you do choose to use the while loop, be careful in how you use it and make sure to use it wisely. All right, let's talk about these statements in greater detail, and I'm gonna point out a few things about them that are uniquely different from what you're probably used to in other computing languages. First off, it looks just like a regular if statement. It has the if, else structure to it. So you have the same flexibility you have with any other if statement in any other language. The one key thing that I think is important to point out is that this word here, else if, is very unusual in the sense that they seem to have forgotten to put an E there. So it's ELSIF without the E, and that is their else if symbol or statement. But it works just like any other statement. You basically, in the if statement, you have an expression that evaluates to a Boolean, true or false. Typically, you would use something like a comparative operator where you would say if this equals that, or this less than or equal to that, and then that will evaluate to true or false. And then when that condition is true, obviously it will execute the statements inside that block. And so in all other respects, it acts exactly like any other language would. The other thing is you can eliminate things. You don't necessarily have to have an else if or an else. You can have a straight if, just like in regular language. You can use else if with no else. You can have an else, with no else if. So any permutations of this that you're used to inside of other languages work fine in VHDL as well. The case statement is a powerful statement, and we'll see a lot of that inside our VHDL descriptions. The case statement starts off with the keyword case, and you'll notice there is an expression that follows that. And then that expression basically has to evaluate to some value. Okay, it's not a Boolean, it's just a value. So it could evaluate to a standard logic vector. It could evaluate to a standard logic signal, an integer value. It doesn't matter. But it evaluates to a specific value, and then that value is compared with the choices that are listed after the choices statement. So right here is where you would list the choices, right? So if we wanted to, we could basically say, if this were an integer, right? So if I were to go in here and kind of play around with this and say this, okay, in case count is equal to 12, okay, then basically the statements underneath there would execute, or if count is equal to 10, then I can do else if it's equal to 10, I could do something else here. So these are choices. I could set up multiple choices by using the pipeline character, and so I could say if it's 12 or 11 or 10 or 9 or something like that. So whatever my goal is for this, I can set in those choices based on what I want, right? So it's very, very similar to what you would see in like a switch statement in C, except one very, very, very important difference is that unlike the switch statement in C, you do not need to break out of the cases. Okay, so these are pretty much self-contained units. If this executes that, then it jumps all the way to the end when it's finished. Okay, so there is no need for a break that you would normally see in another language. Okay, so that's the basics of that. So we see here that the other caveat that I want to mention is that all choices must be mutually exclusive. So you must have unique choices for this to function properly, right? So typically this would be used in a state machine to determine whether we're in a particular state. So that's a specific value, and then we can check that out by just comparing that with the expression and the value over here. So we'll see that in some examples a bit later, okay? All right, so the next one that we're going to look at is the for loop, and this is a looping structure. And this allows you to loop through statements multiple times, depending on what it is you're trying to do, and that will give you the opportunity to loop through 10 times, 20 times, whatever, for testing things. Now, in one of our earlier examples, we had a project where we were counting the number of switches that were active. Well, a looping structure would be just as good for that as the structure that we put in place. In fact, probably better, in the sense that it's more efficient to read and easier to document that way. So instead of going through and individually checking the switches one by one with separate code, we could simply loop through the vector and look at each bit one at a time and then test that out. One of the important things that we want to do is we want to express our ranges for the loop in constants, and this is important for synthesis purposes. If you don't, then you could generate some very, very inefficient logic in your design, and it could create some problems down the road. So you want to make absolutely sure to use constant values as your limits. Now you can express those, and I've got this in the example so you can see that you can use the to or the down to keyword to express those. So in the first loop here, when we look at the first for loop, we're basically taking the iterator I and we're starting at 0 and going to 10. Okay, so 0, 1, 2, 3, 4, 5, all the way to 10. In the second one, we're basically taking the iterator J and we're counting from 8 down to 1. So you can go in either direction, but you'll notice that we have constants on each end. It's not a requirement, but it's a good practice. And so what I'm really showing you here is good practice. Deviating from that, really, there's rarely a need to do that. And so it's probably a good practice just to stick with this strategy. One of the things that's also interesting to note is you don't have to declare an iterator variable in the rest of your code. This is actually the way it declares the variable is through the for loop. So the variable I, for instance, and the variable J don't have to be declared up above here as, variable I or variable J. These are actually part of the declaration of the for loop, creates them, and you don't need to worry about that. Okay, and like I mentioned before earlier, the while loop here, I mentioned that here, is supported, but it's limited for synthesis, and so it can lead you down a path of a lot of headaches, and so I'm trying to avoid that for this, so we're going to focus primarily on the for loop for our discussions here. All right, so one of the things that we've talked about so far is we've looked at the process structure, how it's built. We've looked at the different statements that you can use in the process, the if, the case statement, and then the for loop. And now what we want to do is we want to talk about how you represent values inside of a process. And you can do this by creating and calling a variable. We mentioned that before. Variables can be declared in the declaration area of the process. And then you can declare them just like you would signals, except using the keyword variable. And variables are incredibly different in the way they behave inside a process as opposed to the way signals behave. So, but it will make sense once we talk about the delta cycle model and how circuits are evaluated, and we'll do that soon. But the process of having two things as signals and a variable can be confusing. So what I've done is I've put together some examples of how to declare the variables and how they're used, and then in a minute we'll talk about the differences with signals. So basically, variables can only be declared in processes, functions, and procedures. So these are things that are really within the sequential code area of our design. Variables update instantly when executed. So as soon as a variable gets a new assigned value, that is instant, and then it propagates through the rest of the code. This is the reason I say this is because in signals, in the case of a signal, signals don't update instantly inside of a process. They actually update when the process ends. So variables are incredibly different in the way in which they are updated and the way in which they're handled inside processes. And to reinforce that difference, we use the colon equals symbol to represent assignment to a variable. Remember, when we're assigning signals to a signal, we'll use the less than and equal sign, and that's our signal assignment operator, okay? But this is our variable assignment operator, and it will flag you during your compilation runs that you made an error if you try to assign them wrong. But it is one of those things that you need to keep clear, and once you've done this a little bit, it becomes second nature. One of the other caveats of this is you can actually initialize the values during declaration for the variables, and that can be handy in some cases, but I encourage you to avoid that unless you need it in your design, that initialization. So let's look at how we declare a few of these. Down here we've got our first variable declaration, and it looks just like a signal declaration, except for we have the keyword variable instead of signal. The naming rules are the same with the lower camel case. This is a standard logic vector declaration. We have one down here which is an integer declaration, and notice how when I declare integers I'm putting ranges on them, and we talked about that when we were doing data types, that you want to constrain your integers with a range declaration so that it produces the most efficient hardware for you. Now down here, this area right here would be in the declaration part of the process, whereas this area here would be in your definition part, right after the begin in the process. So I'm declaring a process, giving it a name. Remember, I stressed the names are so important. We have a sensitivity list here, so just random variables as an example here. And then inside the process, I've declared a variable called status. And so that's that has scope inside the process only. You can only see that variable inside the process, and it's used by the process. And here's an example assignment where we just assign it the value 12. So it's just, basically it works like any other storage variable, for lack of a better word, to hold values in your design. But the key differences are it gets updated immediately. So why don't we take a look at that? So this is variables. This is how you declare them. This is how you use them in your design. Why don't we take a look at some of the difference between variables and signals so we can get a better handle on that for our design as we do our designing. Updating values. Variables, like we said before, will update instantly, whereas signals, they don't update until the end of the process. So the process has to terminate or suspend before a signal gets updated. But a variable, as soon as it changes values inside the code, will change values, right? So that's not delayed. And we can take advantage of this, actually. It actually becomes a benefit in some designs. So when we get to state machine design, we'll see where we can take advantage of the fact that signals don't get updated till the end in order to make sure that we're generating combinational logic for our transition processes. So we'll look at that when we get to the state machine. So don't worry if you don't get that right now. The declaration, variables can only be declared inside of processes. So they're inside processes. Signals are declared outside processes as part of the architecture. So you will declare your signals in the architecture, and you'll declare your variables inside the processes. And then lastly, the assignment, that's the assignment operator, the colon equal for a variable. And then of course the less than or equal with is the signal assignment operator. Now we're gonna see in future videos lots of examples of processes and different ways to specify processes. So we'll see some examples, but I wanted to hit all the basics first before we dove into the example realm. And the last thing we want to talk about today is that's a few things about processes that are important for us to realize. Processes describe hardware, and that's critical to understand. A lot of times it's easy to get drawn into the idea that a process is like a program, but it's not. It's actually defining hardware. And so we want to keep that foremost in our mind. Now, a process can actually be represented by a design block. Okay, so that's one of the natures. Let's draw a better box. That's one of the natures of the process, is that it defines a hardware entity that you can kind of think of as a box with inputs and outputs. So the box itself will have inputs just like any other design, and a series of outputs on it. And the process itself will have a name, which we've talked about giving it a name. And so the process name would be specified above the block. And this is the way we would draw this when we're drawing block diagrams of our process, so we can see how it interacts and relates to other parts of the design. So like I said before, the process represents a design block. okay? Processes also must suspend and terminate. We talked about that before. And what that means is you just can't have an infinite loop in a process or have it waiting on some condition. You can't have a process sitting there waiting for someone to push a button or activate a button. Well, you can, but you have to define it properly, right? So you have to define it so that it's using a sensitivity list or it's waiting on a signal change. And we'll talk about both of those later. Statements in a process are sequential. That's obvious. We talked about that at length. And then signals update when the process suspends and terminates. So whenever the process suspends or terminates, the signals will update, and we've addressed that. And then processes without a sensitivity list must contain a wait statement. So we've talked about two types of processes up to this point. We talked about a process without a sensitivity list when we were doing test benching earlier. And we said that if that's the case, we must have a wait statement in there because that suspends the process. That's a requirement. But if the process does have a sensitivity list, then we would not need a wait statement and not use one, and instead rely upon those signal changes to trigger the process to execute again. Okay, so that's pretty much the gist of our little introduction to process basics. We're going to start diving into some more complex stuff later on, so I'm really looking forward to showing you how to become a great digital VHDL designer by exploring all the possibilities of these processes. So we'll see you next time in the next video. Thanks for coming by.